Hello students, welcome all of you. In this video, we will discuss a very important topic in quantum mechanics, Heisenberg uncertainty principle for BSc Part 3 Physics Honors and Physics General courses. In 1927, Heisenberg proposed a very important principle in quantum mechanics, which is the direct consequence of de Broglie relation. 1927 में जर्मन साइंटिस्ट हाइजेनबर्ग ने एक प्रिंसिपल को दिया जो कि de Broglie रिलेशन का डायरेक्ट सीधा नतीजा है या सीधा रिजल्ट है या सीधा प्रभाव है. According to de Broglie, we cannot measure or determine the position and momentum of a particle accurately. If we measure the position of a particle accurately, then there will be uncertainty in the measurement of momentum एंड वाइस वर्सा. हाइजेनबर्ग के अनुसार हम एक साथ किसी पार्टिकल के पोजीशन को एंड लीनियर मोमेंटम को एक्यूरेटली मेजर नहीं कर सकते हैं. यदि हम किसी पार्टिकल के पोजीशन को एक्यूरेटली मेजर कर भी लेते हैं तो उसी समय उसके मोमेंटम, उस पार्टिकल के मोमेंटम के मेजरमेंट में अनसर्टेनिटी होगी, अनिश्चितता होगी. दैट इज मेजर्ड वैल्यू लीनियर मोमेंटम ऑफ द पार्टिकल का, मतलब लीनियर मोमेंटम के पार्टिकल के लीनियर मोमेंटम का जो मेजर्ड वैल्यू होगा वह एक्यूरेट नहीं होगा. यदि पोजीशन का मेजरमेंट उस पार्टिकल का अगर एक्यूरेट हो भी जाए तो उसी समय उस पार्टिकल का लीनियर मोमेंटम का मेजर्ड वैल्यू उसमें डिफेक्ट होगा, वह एक्यूरेट नहीं होगा, उसमें अनसर्टेनिटी होगी. अल्टरनेटली यदि हम किसी पार्टिकल के लीनियर मोमेंटम को एक्यूरेटली मेजर कर लें तो उसी समय साइमल्टेनियसली उस पार्टिकल का पोजीशन का मेजर्ड वैल्यू वह एक्यूरेट नहीं होगा. दैट इज उस पार्टिकल के पोजीशन के मेजरमेंट में अनसर्टेनिटी होगी. नाउ हाइजेनबर्ग अनसर्टेनिटी प्रिंसिपल कैन बी स्टेटेड एज द प्रोडक्ट ऑफ uncertainties in the measurement of position, that is delta x, and linear momentum delta p. Delta p is the uncertainty in the measurement of linear momentum of a particle, whereas delta x is the uncertainty in the measurement of position of a particle. According to Heisenberg, thus the uncertainties in the measurement of position of a particle, that is delta x, and measurement and uncertainty in the measurement of linear momentum, that is delta p, and the product of both, that is delta x multiplied by delta t, is of the order of h cross. But the uncertainties in the measurement of position of a particle and its linear momentum cannot be smaller than h cross by 2. Therefore, Heisenberg uncertainty principle for position and momentum can be stated as product of delta x, which is the uncertainty in the measurement of position of a particle, multiplied by delta p, that is uncertainty in the measurement of linear momentum of a particle, and it should be greater and equal to h cross upon 2. And this is the uncertainty relation, Heisenberg uncertainty relation for position and momentum. डेल्टा एक्स अनसर्टेनिटी है किसी पार्टिकल के पोजीशन के मेजरमेंट में, एंड डेल्टा पी अनसर्टेनिटी है किसी पार्टिकल के लीनियर मोमेंटम के मेजरमेंट में. दोनों का प्रोडक्ट हाइजेनबर्ग ने बताया था कि दोनों का प्रोडक्ट एच क्रॉस के ऑर्डर का होता है, वेयर एच क्रॉस इज इक्वल टू एच अपॉन 2 पाई. बट uncertainties in the measurement of position of a particle and linear momentum of a particle cannot be smaller than h cross by 2. Therefore, Heisenberg uncertainty principle modified as delta x multiplied by delta t is greater than equal to h cross upon 2, and this is Heisenberg uncertainty principle for position and momentum, for the measurement of position and momentum of a particle. Heisenberg uncertainty principle for position and momentum, for the measurement of the position and momentum of a particle, for the position, measurement of the position and linear momentum of the particle. Suppose it is equation number 1. जैसा कि मैंने बताया, डेल्टा एक्स अनसर्टेनिटी है किसी पार्टिकल के पोजीशन के मेजरमेंट में अनसर्टेनिटी है, एंड डेल्टा पी किसी पार्टिकल के लीनियर मोमेंटम में मेजरमेंट का अनसर्टेनिटी है. दोनों का प्रोडक्ट ग्रेटर एंड इक्वल टू एच क्रॉस बाई 2, वेयर एच क्रॉस इज इक्वल टू एच क्रॉस और एच कट इज इक्वल टू एच अपॉन 2 पाई, वेयर एच इज लेंथ कांस्टेंट, वी नो वेरी वेल. Heisenberg uncertainty principle is not restricted to only position of a particle and its linear momentum. It can also be applied to a pair of other conjugate quantities like energy and time, angular momentum and angle. So Heisenberg uncertainty principle for a pair of conjugate quantities, energy and time, can be expressed as delta E, product of delta E and delta T should also be greater than equal to h cross upon 2. And this is equation number 2, and it is the Heisenberg uncertainty principle for energy and time, for the measurement of energy and time, that is delta E multiplied by delta T is greater than equal to h cross by 2. And Heisenberg uncertainty principle for another that is a pair of another conjugate quantities, angular momentum and angle, that is delta J multiplied by delta theta is greater than equal to h cross by 2. Suppose it is equation number 3, and equations 1, 2 and 3 are equations 1, 2 and 3 represent Heisenberg uncertainty principle for position and momentum, energy and time, and angular momentum and angle. That is 3 pairs of conjugate quantities. Now we will prove the uncertainty, Heisenberg uncertainty principle by the simplest method. Alternative methods, alternative proof of Heisenberg uncertainty principle. There are alternative proofs of Heisenberg uncertainty principle, but we will prove Heisenberg uncertainty principle for position and momentum by using the simplest method. So now proof of Heisenberg uncertainty principle for position and momentum. The group velocity of de Broglie waves associated with a particle is capital G equals to d omega upon dk. This is the group velocity of a particle associated with de Broglie waves. Group velocity of de Broglie waves associated with a particle is capital G equals to d omega upon dk. Omega is the angular velocity and k is the propagation constant, which is equal to 2 pi by lambda. Now we can write it as d omega, group velocity of a particle associated with de Broglie waves and or wave packets is capital G is equal to d omega upon dk, and it is d omega upon d. K is equal to 2 pi upon lambda. We can write k as 2 pi by lambda. K is the propagation constant. Lambda is the wavelength. Now differentiation of 2 pi by lambda. 2 pi is constant, so it is taken out of the symbol, taken out of the bracket. That is 2 pi is constant, and d of then we have d of 1 by lambda. Differentiation of 1 by lambda. 2 pi constant है, उसको ब्रैकेट से बाहर कर दिया गया डिफरेंशिएशन सिंबल से. So 2 pi into d, differentiation of 1 by lambda, and it is now d omega upon 2 pi, and differentiation of 1 by lambda is minus 1 by lambda square, minus 1 by lambda square, and d lambda multiplied by d lambda. So differentiation of 1 by lambda is minus 1 by lambda square into d lambda. And in the next step we can write group velocity of a particle capital G equals to minus lambda square, 1 by minus 1 by lambda square. तो lambda square अब न्यूमरेटर में चला जाएगा, तो minus lambda square upon 2 pi into d omega upon d lambda. Suppose it is equation number suppose it is equation number A. Now we know the de Broglie relation, since Heisenberg uncertainty principle is the direct consequence of de Broglie relation. क्योंकि Heisenberg uncertainty principle वह de Broglie relation का नतीजा है, या de Broglie relation का रिजल्ट है, परिणाम है, या de Broglie relation का प्रभाव है, कंसिक्वेंस. उसे कंसिक्वेंस का मीनिंग रिजल्ट, इफेक्ट, परिणाम, प्रभाव. तो ग्रुप वेलोसिटी g इक्वल्स टू माइनस लैम्डा स्क्वायर अपॉन 2 पाई मल्टीप्लाइड बाई d ओमेगा अपॉन d लैम्डा. नाउ de Broglie relation we know as de Broglie relation is lambda is equal to h upon p. This is de Broglie relation or de Broglie relation. De Broglie relation is lambda equals to h upon p. Suppose it is equation number B. Now we can differentiating both sides of B, de Broglie relation. We will get d lambda equals to h is constant. So differentiation of 1 by p equals to minus 1 by p square into dp. So differentiating b, we will get therefore d lambda differentiation of lambda in LHS of de Broglie relation is lambda. So differentiating both sides of de Broglie relation given by equation B, we have in LHS it is d lambda equals to h is Planck constant. H is Planck's constant, so it is constant, and differentiation of 1 by p is minus 1 by p square into dp. So it is now in RHS we can write differentiation of h into differentiation of 1 by p is minus 1 by p square into dp. Now substituting the values of d lambda and lambda from suppose it is equation number C. After differentiating de Broglie relation lambda is equal to h by p, we get d lambda equals to h multiplied by differentiation of 1 by p minus 1 by p square into dp. Now substituting the values of lambda from the de Broglie relation lambda is equal to h by p from equation B and d lambda from equation C after differentiating de Broglie relation in equation A, that is expression for group velocity, we get capital G equals to, in place of lambda we can write h by p. So h by p square is h by p, lambda square is h by p का whole square, that is h square upon p square. So now equation A becomes, using equations substituting the values of lambda and d lambda from equations B and C in equation A, we have using equations B and C in equation A, we get group velocity of a particle is capital G is equal to minus lambda is h by p, lambda square है h by p square, that is 1 by 2 pi multiplied by lambda square by 2 pi, so it is 1 by 2 pi multiplied by lambda is h by p का whole square, so h square p square multiplied by d omega upon d lambda का वैल्यू है h into minus 1 by p square into dp. So it is minus h upon p square into dp. Now p square and p square will cancel out, and h in the denominator and h square in the numerator. 1 power of h square in the numerator will cancel out from the h, a small h, Planck's constant in the denominator. न्यूमरेटर में h स्क्वायर का एक पावर डिनोमिनेटर में h का एक पावर से कैंसिल होकर के न्यूमरेटर में एक पावर h का होगा, मतलब केवल h बचेगा, और p स्क्वायर से p स्क्वायर कैंसिल हो गया, माइनस माइनस प्लस, सो वी विल गेट, नाउ वी गेट h अपॉन 2 पाई इंटू d ओमेगा अपॉन h अपॉन 2 पाई इंटू d ओमेगा अपॉन dp. we get h upon 2 pi multiplied by d omega upon dp. d omega upon dp, and h by 2 pi we know h cross, so it is h cross, h by 2 pi is h cross or h cut into d omega upon dp, and this is capital G, this is group velocity. So group velocity equals to capital G, group velocity is h cross multiplied by d omega upon dp, and it is equation number D. As we know that group velocity is the velocity of a particle associated with de Broglie waves or de Broglie waves or wave packets. So since we know velocity is dx upon dt, so velocity of a particle is dx upon dt or delta x upon dt, that is average velocity. So velocity of the particle is v is equal to delta x upon delta t. It is the velocity of a particle. Now this group velocity is also the velocity of a particle associated with de Broglie waves. So we can write g is equal to v. room velocity is equal to the velocity of the particle delta x upon delta t. So equating both, we have v is equal to g. Therefore capital G is equal to v, or v is equal to g, and v is delta x upon dt. We can write it as dx upon dt also. So dx upon dt in place of delta x upon delta x upon delta t, and it is equation number E. V is equal to delta x upon dt. It is the average velocity, instantaneous velocity dx upon dt. So dx upon dt, we can write dx upon dt. If time interval delta t is very small, then we can write delta x upon delta t as dx upon dt also. So now we have equating, that is g is equal to v, or v is equal to g, or v is equal to delta x upon delta t equals to capital G is equal to h cross upon d omega upon dt. In place of d omega upon dp, we can write delta omega upon delta p. If delta p is very small, that is uncertainty in the measurement of position is uncertainty in the measurement of momentum of a particle is very small. That is if delta p tends to 0, then we can write delta omega upon delta p as d omega upon dp. So d, in place of d omega upon dp, we can write delta omega upon delta p. So we have our delta x upon delta t equals to h cross delta omega upon delta p. d omega upon dp को हम डेल्टा ओमेगा अपॉन डेल्टा पी लिख सकते हैं, एंड डेल्टा पी का लिमिटिंग वैल्यू अगर बहुत स्मॉल है, डेल्टा पी लिमिट डेल्टा पी टेंड्स टू 0, तो उस सिचुएशन में लिमिटिंग वैल्यू ऑफ डेल्टा ओमेगा अपॉन डेल्टा पी को हम डी ओमेगा बाई डी पी लिखते हैं. और नाउ वी हैव डेल्टा एक्स into delta p. After cross multiplication, we have delta x multiplied by delta p equals to h cross multiplied by delta omega multiplied by delta t. Delta omega is the uncertainty in the measurement of angular velocity. Delta t is the uncertainty in the measurement of time, or very small time. Delta t is time interval delta t. Delta omega is change in angular velocity, or uncertainty in the measurement of angular velocity. Delta t is the uncertainty in the measurement of time. Another form of Heisenberg uncertainty principle for two other conjugate quantities, energy and time, is delta E multiplied by delta T. Delta E is h nu, where h is Planck constant, nu is the frequency, and 2 pi times the frequency is angular frequency. So product of delta omega and delta t should also be greater than 1. Therefore we have the relation delta x cross delta p, and since product of delta omega multiplied by delta t should be also greater than equal to 1, therefore we have the result delta x cross delta p is greater than equal to h cross, but we know that the uncertainties in the measurement of position of a particle and linear momentum, that is delta product of delta x and delta p cannot be smaller than h cross by 2. So we can write here since delta omega into delta t must be greater than equal to 1, therefore this relation is delta x into delta p. Delta x is the uncertainty in the measurement of position of a particle, and delta p is the uncertainty in the measurement of linear momentum of a particle. तो दोनों का प्रोडक्ट निश्चित रूप से, क्योंकि डेल्टा ओमेगा इंटू डेल्टा टी का जो प्रोडक्ट होगा 1 से ग्रेटर होगा, इसलिए डेल्टा एक्स इंटू डेल्टा पी का जो प्रोडक्ट होगा, अनसर्टेनिटी, द प्रोडक्ट ऑफ अनसर्टेनिटीज इन द मेजरमेंट ऑफ पोजीशन डेल्टा एक्स एंड इन मोमेंटम अनसर्टेनिटी इन द मेजरमेंट ऑफ लिनियर मोमेंटम इज डेल्टा पी, तो दोनों का प्रोडक्ट डेल्टा एक्स इंटू डेल्टा पी इज ग्रेटर देन इक्वल टू, it will not equal to h cross into delta omega into delta t, because delta omega into delta t should be must be greater than greater than equal to 1. Therefore this relation becomes delta x multiplied by delta t greater than equal to h cross, but the uncertainties in the measurement of position and linear momentum of a particle cannot be smaller than h cross by 2. So in place of h cross we can write h cross by 2. So delta x multiplied by delta t, that is product of uncertainty in the measurement of position of a particle delta x and uncertainty in the measurement of linear momentum of the particle that particle is delta p should be greater than equal to h cross by 2, that is h upon 4 pi. H cross is h upon 2 pi multiplied by 2, that is h upon greater than equal, we can also write it as greater than equal to h upon 4 pi. And this is proves the Heisenberg uncertainty principle for position, for the measurement of position and linear momentum of a particle, that is delta x multiplied by delta t is greater than equal to h cross by 2 or is greater than equal to h upon 4 pi, where h cross or h cut is equal to h upon 2 pi. This is the simplest method to derive Heisenberg uncertainty principle, which we have done in this video. There are alternative proof of Heisenberg uncertainty principle also. Now this video is completed. Thanks all of you for watching my YouTube channel Physics Quantum Classes.